This is a quick video about the equation that lets you find the distance of an object from a center point using two receivers and a beacon. So you know D2 and D1, and you know D3 between your two beacons. And this is the same thing that lets you judge distance with your eyes because they're set apart. So math is actually pretty complex. Probably have some of it wrong, but it works in Desmos. We're using the law of cosines and the law of sines to jump between the angle and the side. So D4 represents the distance from your center point, from your two receivers to the target, while D2 and D1 are your actual inputs, while D3 is a constant. And you just drop them down here, and as D2 and D1 change, D4 is produced. A quick overview of how I built the equation was first I used the law of cosines to break it out because we have all three sides, and that gives me the theta at the top of the pyramid right here. And using that theta, we then can use the law of cosines, which relate the every D1's length over the sine of theta 3 in this example would be equal to D2's length over the sine of theta 2. So using that, we do this equation and we solve for theta 2, which comes down here, and then we use the line of cosines again to solve for D4, which is now solvable. And all of those collapse into equation looks like this. Each one of those steps in Desmos also looks like this. So this is the actual final equation for solving for D4, and you see an output right here of 23.6. And I actually tested and confirmed this on the board by measuring out each side of that triangle, and you can see I measured it as 24.5, so it's pretty close. And I plugged in D1, D2, and D3, which are your inputs. See, D1, D2, D3, and out pops pretty close your right magnitude. So it's like it's a distance calculator essentially. I also can find you the theta right here, theta 7, that this line creates, so you can see how far and where it is for your target at least. That's represented by this right here, which is the law of cosines again, and you have D3 over 2 squared plus D1 squared minus D4 squared over 2 times D3 over 2 times D1. D4 we've solved for, so we're going to plug in this whole thing right here, and D3 we divide by 2 because we take it from the middle, so D3 over 2 is equal to just one leg right here. So the final theta equation for D4's angle looks like this, and you can see I'm converting it to degrees over there so it's easier to read. And we have about 67 degrees, and this is for the triangle right there on the board, and you can see it's pretty accurate. What I like about this equation is you can actually change D1 and D2 in real time, and it's kind of like the triangle's legs extending or retracting, and it moves the focal beam back and forth, the focal point, and you can see that reflected in the angle right here. So if we decrease D2, the angle should increase. So we'll take, where's it, D2, there you go, and there you go, pass through an origin. Or if we increase D1, there we go. Sometimes I make impossible triangles that don't work. So as we decrease D2, you can see down here, oh, that's horrendous. I'm not dragging it. Holy smokes, Batman. There you go. So you decrease it, angle's going down. That makes sense, because, yeah. All right, I think it's actually inverted, but I swear this is the theta. It worked right before this. But yeah, no, this is the theta equation, so let me back up. There you go. And for funsies, test it again. So let's do D1 is 18, D2 is 11.4, like this, and that's actually measured. We have an estimated side length of 14.25 from the main equation with an angle of 35.8 degrees. So I measured, and this is in fact very close to 14.2. It's 14. I just measured with a ruler, and I would say this is probably about 35 degrees. Yeah. So I hope this video is helpful. Godspeed.